Welcome everybody to the webinar of today. The speaker of today is Jens Eggers, and he's going to talk about theory of bubble tips in strong viscous flows. As usual, I introduce the speaker very briefly, and then I leave him the floor. So Jens Eggers is a professor of applied mathematics at the University of Bristol. His career has been devoted to the understanding of self-similar phenomena. He has made fundamental contributions to our mathematical understanding of free surface flows, in particular breakup and coalescence of drops. His work is instrumental in establishing the study singularities as a research field with dynamics and applied mathematics. Dr. Eggers has also worked on non-Newtonian flows, as well as granular flows, thin films, contact lines, and nonlinear elasticity. He continues to have an interest in statistical physics, most recently dynamic interest in glasses and gels. He's a member of the Academy of Arts and Sciences in Erfurt in Germany, a fellow of the American Physical Society, and the recipient of the Stanley Conris Award of the American Physical Society. So it's with great pleasure that we have here Jens Eggers for the seminar of today. So Jens, I stop sharing my screen. And if you want, you can start sharing yours.
Yeah, Francesco, thank you very much for the kind introduction. Yes, so I will talk about a subject area I've been interested in for a long time and would like to tell you a little bit about some recent progress. Basically, the physical question I'm asking is, if a free surface is deformed by a viscous flow, how strongly can you deform this surface? So the viscous flow wants to curve the interface, whereas the opposing force of surface tension wants to keep the interface straight. And the question is, what's the result of the balance between these two forces? So to give you some examples of these axisymmetric flows I have in mind, let's start with Taylor's famous experiments of bubbles or low viscosity drops in a viscous flow. The viscous flow was driven by some system of rollers, and Taylor observed that the shape of the drop at the end here could be focused into a very, very sharp tip. A similar phenomenon occurs if you have a bubble rising in a viscous fluid. In a real world seminar, I also like to show shampoo bottles, where you can do the experiment yourself. You just turn the shampoo bottle and you see that at the rear of the bubble, you again form very, very sharp tips. And as a third example, I mentioned the selective withdrawal experiment. These are experiments I did a long time ago with Sylvain Courrèges-Dupont, now at the University of Paris, where you can imagine you have, again, a bubble hovering over a drain. And once more, the fluid flow, you can imagine here, which goes past the interface between air and liquid, forces the interface into a very sharp tip. And we, at the time, did very careful measurements of this interface, and I'm going to show some of these results later. More recently, there have also been lots of applications of these things in microfluidics, where generally the idea is to use small-scale flow to force an interface into various interesting shapes. These axisymmetric shapes I'm talking about here, okay, but I forgot. Let me give a few more exotic examples where you might want to use these very tipped shapes to create permanent objects. So, for example, here, apparently fluid was, air was driven into this glass, and as the glass cools, you preserve this very sharp tip structure. Or here you have a nice picture of a bakery product from France, where also you have produced a very sharp tip. So these are all axisymmetric or close to axisymmetric objects, which will be the topic of my seminar today. There is a two-dimensional counterpart of what I'm talking about, discovered mostly by Keith Moffat in Cambridge, where you try to keep the flow mostly two-dimensional. And you do that by having a roller in a liquid bath, and the flow driven by the roller is essentially two-dimensional. So the interface here is a ridge that you have to imagine is continued into the board, and you can use a two-dimensional description to describe the flow. So Jonathan Moffat solved the Stokes equation. This is the viscously dominated version of fluid mechanics to find solutions in two dimensions near this tip here. And they found that the shape of the interface is actually, well, this is, you cannot see it that well here. The shape of the interface is actually best described as a cusp. And they found that if you look at the radius of curvature of the tip, which I call R here, they found that it decreases very rapidly, namely exponentially, with the strength of the flow, where the strength of a viscous flow is usually measured by the capillary number, and the capillary number is always a flow speed times the viscosity divided by the surface tension. So if you see a capillary number, you should always just think of a flow speed in some dimensionless form, which takes care of the surface tension. And now the question will be, if I have an axisymmetric flow, what will the corresponding relationship be? Will I be able to force my interface even stronger? Or is my interface relatively smooth? I mean, the very first question is, is the interface smooth at all? Or am I perhaps, by forcing it with a viscous flow, am I able to produce a true singularity? And if there is always a finite curvature, the question is, how does the curvature increase if I increase the flow strength? So these are the main scientific questions I will ask. So this is quite an old subject. I showed you the publication of G.I. Taylor from the 1930s. In the 1960s, G.I. Taylor again devised an ingenious theory for the deformation of an axisymmetric interface by a viscous flow using what's known as slender body theory. So slender body theory assumes that the shape I'm describing is slender. So this extension here in this direction is much greater than the extension here in the radial direction. And this assumption permits to describe the flow as a superposition of singularities, which are concentrated here on the axis. And I use this insight to get an equation for the interface. So I'm not going to present this theory in detail here, But what G.I. Taylor found was that the interface here at the tip is conical in shape. That's what the slender body theory gave. And since it's a cone, it ends in an exact tip with infinite curvature. So that's the reason why it's actually relevant to ask whether the interface has infinite curvature or whether it remains always rounded. And this calculation was then later extended to the next order, which is something I will come back to later. But let me, in some sense, begin with some of the results I'm going to get to make you aware of what the issues are. So what I'm doing here is I compare the results of G.I. Taylor. The result of G.I. Taylor near this end here corresponds to a cone. So if I look at the interface, if I look at the thickness, the radius h here as a function of the distance from the tip, G.I. Taylor's theory would predict that the interface is a straight line. And in these panels here, I've always shown the same thing. I'm just showing it at different resolutions. So here I have the neighborhood of this tip here on a scale of 1. Here I have the neighborhood of this tip on the scale of 10 to the minus 2, so 2 orders of magnitude smaller. And here again, 2 orders of magnitude smaller. And I take this here from numerical simulations of the full problem, of the full solution of the Stokes equation with such a bubble surface present here. So G.I. Taylor's theory would predict that the slope here is always the same, independent of the resolution because it's a cone. But what our simulations showed was that the real interface actually looks a little bit like a cone, which is also what we've seen in the experiments. But if you change the resolution of the resolution with which I'm showing the interface, the slope changes slowly. So if I go closer and closer to the tip, the slope increases more and more. And if I go away from the tip, the slope of the interface decreases slowly. And that's something to keep in mind. That's an insight my theory will actually be based upon. So how do I approach this problem? The first thing I'll do is to introduce a description which is local around this tip here. And I do that by introducing a similarity solution. So here is a close-up of this tip here. But what I've done is I've written both axes here in units of the curvature of the tip. So kappa m is the mean curvature of this bubble tip. And I've written both the radius here and the distance from the tip in units of the inverse curvature. And this already indicates that in actual fact, I want to describe a theory in which the curvature remains finite always. So instead of the original interface h of z, I will be describing a similarity profile capital H of zeta, where everything is in units of the curvature. So just to make sure you keep an idea of where I am in my description, let me give you, a very simplified back of the envelope description of what I will do. So the physics of this problem is that at the tip here, there is an interplay, a balance of the outer flow, which is this flow in black here, which goes to the left. And this flow is balanced by an opposing flow, which comes from the capillary retraction of this tip here. And if these two balance, if the flow going to the left and the retraction balance, then I'll have a stationary interface, which is what I'm looking for. So the difficulty is to calculate the speed of retraction, and I'm going to show you in a minute how you do it. But essentially, what you find is, and that along this interface, you have to keep into account the contributions to this retraction coming from all scales. So the speed of retraction here is actually not a local expression, but it's an integral over this interface, where L is a variable I will use a lot. It's the logarithm of the distance from the tip. So it's always the logarithm that will come into play here. S here turns out is the local slope of this interface. The radial component of the velocity I can get through an analogy with a radially symmetric collapsing cavity, and that's a relatively simple problem to do in Stokes flow, and I find that the radial component of the velocity is a constant, and that's given by the capillary speed, which is the surface tension divided by the viscosity. And when I have the radial and the axial velocity, I can relate that to the slope. And from solving this set of equations here, one can see, which is something I will, in a second, I will do in a little more detail, is that the local slope goes like 1 over the square root of L. And that's precisely what I'm trying to show you in the first slide. Namely, the slope varies very slowly on a logarithmic scale. And here it's actually shown that the way in which the slope varies is like 1 over the square root of the logarithmic distance from the tip. So the farther away I am from the tip, the smaller the slope becomes. And that's something I will use later on in my mathematical description. So my mathematical description is actually based on what's known as the boundary integral description, and that's shown here. I hope you're not all having this little panel here in front of the overlaying my my slides.
No, we see the slides.
You just see the slides. That's good.
Yeah.
You know, I have a little annoying band or in front of in front of my. That's good. Okay, so I'm solving the Stokes equation, which is the viscous inertialess limit of the Navier-Stokes equation. There is an ingenious way to solve this equation by thinking of an interface in the following way. If a flow is driven by surface tension, I can look at the free surface here as a superposition of delta functions, where each delta function corresponds to the force, or to the stress, I should say, exerted by the surface tension as at that point. And so using the linearity of the Stokes equation, I can then write the total velocity field as a superposition of those points which are proportional to the mean curvature, because it's known that the surface tension forces are proportional to the mean curvature of the interface. So that's what the first part of the equation is saying. And then there's a second, a little more annoying part of the equation, which unfortunately contains the velocity itself. And the second part of the boundary integral equation accounts for the fact that there is a jump of viscosity, the value of the viscosity across here. And throughout this lecture, I will soon assume that the outer fluid is viscous, whereas the inner fluid is totally inviscid. So you can think of the inner of this object here as a bubble containing air. And this jump in viscosity is accounted for by this second term. And the integral goes over the full surface of this drum. So the nice thing about this description is that I've accounted for the velocity field. The only thing, the only unknown is the interface. The annoying thing is that if I want to do these integrals, I don't know yet what the interface is going to be. That's part of the solution. So this is what I'm up against in trying to solve this equation. But the first step, the first thing you do to solve this equation is first you perform an integral, an azimuthal integral over the angle here, assuming this is an axisymmetric object. So as a result, you only have an integral over the z variable. And then you make a second transformation I've indicated before. I transform to logarithmic variables. So this L here is the logarithm of the distance from the tip. And as a result of this transformation, I have these factors of zeta appearing in my integral. So here it is again. That's the definition of L. And these k hats and j hats are integral kernels, which are functions of two variables, L1 and L2, which I can calculate, and I say a little bit more about them later on. And what I want to do is I want to find the profile H of zeta I've introduced before. And since this profile I know is almost conical, the trick is to write it as a cone. This is a cone here of constant slope s, but the slope s is actually varying slowly on the scale of a logarithm of zeta. So this is the framework. So symbolically, I want to solve the following equation. I think of this as a matrix equation for the Z and R component of the velocity. And I have to perform these integrals, which are right here symbolically as Vzj and Vrj and K1, K2, K3, K4. But I do have to remember that these here are actually not numbers, but are integrals. But the first step is going to be to actually turn these integrals into numbers by realizing that the main contribution to the integral comes from a diagonal term, as I will explain now. So this is the crucial, on a technical level, this is the crucial slide where I explain how I deal with these integrals and how I turn them into something that's simple, like a number. So let's just consider two integrals I want to do as examples. So let's first look at the J integral here, which represents the action of surface tension. So that's why here I have the curvature appearing, the curvature kappa, and I have to perform a convolution of this curvature with this kernel J. And this kernel J here I'm showing here. And you see that if I'm looking at this integral as at a certain fixed L1, the integrand is very sharply peaked around this point L1. The only problem is that this is not quite the case. There's also here in red this long tail. So for large values of L, this kernel actually does not decay that quickly. To simplify the expression, I use the fact, I anticipate that the slope actually becomes small for large values of L, and I'm using this fact to simplify the expression for the mean curvature. The mean curvature then just becomes 1 over S2. And similarly, I can simplify the expression for the kernel, which is this red line here, which turns out to be behave just like the slope squared over 4. And from this expression, you see that this integral here is actually divergent. So this total integral here goes like S2. S2 goes like 1 over square root. And so 1 over square root is not integrable. So this integral here is actually dominated by the upper limit here, which is controlled by the curvature at the tip. So this is an integral I can easily do. The integral over 1 over square root is a square root. So I get that this contribution from surface tension is actually dominated by the upper limit. And this inside here is, in some sense, exactly what I've showed you before. This is the part that describes the capillary retraction of the tip. So now let's come to the other integral I want to show you. That's one of the K integrals. So here you have a convolution of the velocity field itself with some kernel KZZ, which is shown here. And so here, that's actually a nicer situation, because you can see here that if you are at a given value of L1, your kernel is highly localized at the given point L1. So I can do the integral just by taking into account the contribution from this tip here, from this spike, and I can turn the integral into a local expression, a number. And so since I have this narrow peak, instead of the variable L2, I can introduce the variable delta, which is L2 minus L1. And since the main contribution just comes from this one point, I can replace the argument L2 in the velocity by L1 and pull the velocity here in front of the integral. And the remaining integral here is just a number I have to calculate. So how I calculate this integral, I'm not going to show you in great detail, but the idea is that for small slopes, this peak here becomes narrower and narrower, and I can perform an expansion in the narrowness of this peak. And if I do that, I can reduce the integral to something simple, which is just a function of one single variable. And not only that, once I've done that, I can actually do the integral. And the integral, the value of the integral, it turns out is just 1/2. So I've succeeded. I've calculated this K1 here. And this K1 is just a simple expression in the velocity itself. And doing this for K1 and for the other integrals as well, I can actually turn the integral equation I've advertised before in some simple expressions. So here, this here is turns out the R component of my integral equation, but in this localized form. This here is what I've shown you earlier when I did the equation, when I presented you the solution on the back of an envelope, as it were. That's the Z component of my integral equation. And then I got a kinematic condition, which tells me that the ratio of VR divided by VZ should be the slope of the interface. And it's an easy exercise to solve this set of equations here. And the result is that the slope of the interface goes indeed like 1 over the square root of the log of L with some constant of integration L0 here. And likewise, then I can calculate the components of VZ and VR. So this is the result of my calculation to leading order for small s. Let's try to compare it. So these are the old experiments by Sylvain Courrèges Dupont, performed about 20 years ago in Bristol when he was postdoc. Here at the time, we didn't have a theory for it, but let me explain. So the black line here is the result of a full numerical calculation of the problem I've done. The dashed line is the result of this calculation I'm showing you here. So you see it works extremely well, except in a region very close to the tip. And the different colored lines here is the result, without adjustable parameters, of these old experiments at different values of the curvature. And the curvature is varied simply by varying the flow strength. So in this selective withdrawal experiment, essentially what you do is you bring the bubble closer and closer to the orifice, and that increases the flow strength and makes the curvature higher. And so, and this is a summary of of various experiments here at different curvatures, and they all fall onto the black line, except, of course, if you're too far away, because this is a theory that's made just for the tip region. And I can also, this is the shape of the interface, so this is very good. But I can also look at the expression for the tip curvature. This is an expression I've showed you before. I can perform this integral now. You see that this dependency on L cancels, and instead what remains is an expression for the curvature of the tip, where L is a typical length scale of the problem, which I don't know at the moment. I will come back to that in a little while. But the exciting thing is that the prediction is that the curvature of the interface behaves like an exponential to the capillary number squared. So this is exciting because this is a lot more singular than what we had in 2 dimensions. You remember if you have a 2-dimensional cusp, we found that the curvature increases like the exponential of the capillary number. Here, it increases like the exponential of the capillary number squared, so the curvatures get a lot higher. And the reason intuitively is that if you are, I don't know whether you can see my hands, if you focus a flow in 2 dimensions, you're focusing along a line, whereas here we're talking about an axisymmetric object. So we're focusing the flow onto one point coming from all directions. So that's a more effective way of focusing the flow, and that's the reason why you get this more singular expression. And this is a comparison. So the black line is a numerical simulation of the full problem. The symbols are the results of experiments, measurements of the tip curvature. So this is the capillary number at the tip squared as a function. And here is the logarithm of the curvature. And the dashed line here is this result of the theory so far. So you see it's pretty good. It seems it's a little bit steeper than what's observed in experiment. And the other problem is I don't know yet what this length scale L is. And to explore this, to help with this, I will very briefly show you how a calculation can be done to the next order. So this will be a slightly more complicated calculation. So you're not at all supposed to follow the calculation I'm going to give you. I just want to give you a flavor, an idea of what kind of things are involved in doing this calculation at the next order. Because to my mind, it's really an exciting calculation. But please don't worry about following all the details. So the idea is, of course, to do it to the next order. So far, we've expanded in the limit that the slope is small, L is large, and the slope goes like 1 over the square root of L. Now I'm going to include the next terms and try to keep systematically all the terms of the next order. And that's quite technical, as you're going to see here. So the idea then is I have to expand everything. So as I expand about this localized tip I was showing you, I have to expand systematically about the place S1 of the center of the tip, and that will involve derivatives of the slope. And then I have to plug this into the equation and keep all the terms. So this here is an expansion of the curvature. This is the leading order term we've considered before. And these are all corrections which come from the fact that I'm not exactly at the center of the tip, but also taking into account contributions which are a little bit in the wings of the tip. And formally, I can write all of this as a number of integrals. In this case, 5 different integrals, which I all have to evaluate. And I should say the point of the reason I can do these integrals, I can perform these integrals, is that I'm looking at this problem as the interface being a cone, being of cone shape, but with very slowly varying slope. But in this local approximation, I can pretend that the interface is a cone, and these are integrals it turns out I can do. So again, it's a technical point. The integrals I do by what's known as a matched asymptotic expansion. There is an inner expansion which takes into account the center of the peak, for which I use this variable which I've introduced before, and I have another expansion that takes care of the wing of the tip, and I have to combine the two in a matched asymptotic expansion, and that gives me a typical result like that, where here I've already included the terms of next order. And it's perhaps of interest that you get more complicated expression. You not only get the slope, but you also get the logarithm of the slope at the next order. And as I've mentioned, there is another trick to do these integrals over cones. So if I do these integrals over cones, I get these horrible, at least I found them pretty complicated integrals, where the integrand contains itself elliptic integrals. So K and E are names for the elliptic integrals. And just of interest, the way I am able to perform these integrals is because this is something people who use these boundary integral methods know. There are exact relationships for appearing in these integral descriptions, which essentially are expressions of Gauss theorem. So if I integrate the kernel here over any surface in this form, I get the identity matrix. And I discovered that by combining lots of expressions I get of this form, I can actually represent this complicated integral here and find the solution. And in this way, I was, for example, able to show that this integral here, you see here, is nothing but just 1/2. So these are all technical points. I just want to highlight to give you a flavor of what's going on. So if you include all these terms of next order, then you get this set of equations here. The leading order expression I've shown you before, but now I got all these higher order terms here. And I can solve this, and I get my expression to the next order. So this is the leading order I showed you before. S goes like 1 over the square root, but now I also have the next order I get by systematically solving this set of equations. And here I've just compared this next order expression with my numerical simulations, and it works extremely well. So there's one more thing to do now. This is just the description of the near tip region. I also want to describe the whole drop. And for this, I have to match this description of the tip region to an outer solution which describes the whole drop. And as an outer solution, I take the slender body expression I've referenced before, which was again done to second order by Buckmaster in 1972. And I can't go into detail here. I expand the profile and the slenderness to get an expression for the interface. And I've already, for the purposes of matching, only included terms which are relevant near the tip here. So the name of the game here is that of asymptotic matching. In an asymptotic matching, you take the outer limit of the inner expansion. This is what this is my calculation I've shown you. And you try to compare it to the inner limit of the outer expansion. And I require that the two give the same answer. So these are the two expansions, the outer limit of the inner expansion. Before I showed you the inner limit of the outer expansion, and comparing the two, I get an expression for epsilon, where epsilon is nothing but the capillary number, the inverse of the capillary number at the tip. And so I can invert this expression, and I get an expression for R, where R is essentially the curvature at the tip. So this is it. What have I done? I succeeded in writing the curvature at the tip as this factor of e to the 4 capillary number squared as before. But now I've also calculated this prefactor c here, which previously was unknown. And this factor c is this strange combination which in itself contains the capillary number. And now here is a comparison between my full numerical simulation, which is the full line, and this asymptotic calculation. And that's pretty remarkable here. The agreement I get between the full numerical simulation and this asymptotic calculation, where the agreement is supposed to work for large numbers of the capillary number. You should look here. And there are no adjustable parameters here. So this is a remarkable agreement of the second order calculation and the full numerical simulation. And this really is all I wanted to show you. I just wanted to remark that I think these results are of interest, for example, in the science of microfluidics, and where I'm, among others, I try to use flow to force an interface between two fluids into a very sharp tip, out of which comes a jet. And this often, the decay of this tiny jet into droplets is used to create tiny particles, which you can use in applications. So thank you very much.
So thank you, Jens, for the very interesting seminar. So I would say maybe we can open the stage for questions, and I invite all the participants, just feel free to unmute your mic and ask a question if you have any. So maybe I can start.
Yeah.
Actually, it's in the last slide you presented before this, where you compared the asymptotic theory to the simulations, and you had this one. In this parameter, there is, in the parameter C that you computed by matching expansions, there is actually, the parameter C depends itself by the capillary number at the tip, as you as you pointed out. Can you comment a little bit on this? Because I mean, does it kind of match the connection between planar flows and axisymmetric flows, or how would it work in comparison with that?
Well, I mean, what it means in practical terms is here is if I plot things like that, like here, then this exponential would just be a straight line, whereas this here means that, again, the slope of this interface here is slowly varying. And that's what you see here. The dashed line is the first order result I've shown before, which would have a constant slope. And if you look closely, you can see that the slope is slowly varying, and that's what you also see that's what the simulation also does. I mean, it is a reflection of the more complicated structure, I would say, of the interface, where you have, again, in the shape of the interface, you have a similar phenomenon in that you have a slope which is slowly varying on a logarithmic scale, and you don't, in terms of the curvature, you don't see that at leading order, but at next order, essentially, you see a coupling between different regions of the interface, and that's the reason why these extra logarithmic terms are coming in. And since you ask about the 2D case, in the 2D case, you don't have that.
You don't have, yeah, exactly.
You don't have any logarithms. In fact, the whole solution in 2D is of a generic shape, which you can predict or understand just based on singularity theory. It's a generic bifurcation you get, which gives you this cusp form, which is all in a form of power laws, and there are no logarithms there involved. So
yeah, that's
very different.
Yeah, so basically an axisymmetric cusp in a cusp in an axisymmetric bubble is essentially different from the yeah. And I do have another question, but let's see if there is someone else who would like to ask one, and just feel free to unmute your mic once again if you have any question.
Just a quick question. At what scale, or at perhaps even what temperature, does your fluid mechanical description of these cusps and cones breaks down?
Well, that's a good question. I mean, you get that's not known. I mean, because of this very strong dependence on the flow strength, you quite easily get objects which presumably, if you take these approximations, are of molecular size, and presumably if you go to a radius of curvature of you know, a few nanometers, then the hydrodynamic description will break down, and it's not known precisely how best to describe the interface in this limit, or whether there are any special effects that come into play, because the tip has become that small. I mean, that would be an interesting question to investigate in more detail. And in particular, in my case here, where you have a quadratic dependence on the coupling number, it's even easier to get into a region where the size of the tip is effectively zero from a continuum perspective.
I guess people do experiments with this. I mean, do they vary the temperature, for example?
The temperature, not that I mean, on the level of my description here, that temperature wouldn't make a difference. I mean, it would only change the viscosity, I presume, but other than that.
And the surface tension as well?
Yeah, a little bit, but mainly, I mean, for a viscous fluid, typically, I mean, the strongest dependence is typically on the viscosity, I would have thought. I mean, generally, I would think. I mean, and the other effect, of course, is fluctuate. I mean, if presume, I mean, there's a, what I've written here is the deterministic equation. I mean, there are fluctuations, there are thermal fluctuations, of course, which would increase. And that's something in other problems I've worked at related to drop breakup. There are in that case fluctuations actually do play more of a role. I mean, I haven't investigated it. My intuition would be that in this case here, surface tension forces are so strong that thermal fluctuations are relatively minor, but I could be wrong. I mean, it could be that in principle that thermal fluctuations trigger instabilities, or so, for example, that you get things flowing out of the tip, that you get a jetting transition mediated by thermal fluctuations. I can't exclude that, but I haven't. But you're right. The scales near the tip can be arbitrarily small, and you can easily get to a scale on the scale of thermal fluctuations. Absolutely.
Thank you very much. Thank you.
So thank you. Maybe we can see if there is someone else who would like to ask a question. So once again, just feel free to unmute your mic if you have a question. If not, then I can ask you another question regarding actually the example you presented at the end, where you said that actually this theory could be potentially applicable to microfluidics, right? And
yes.
So in this case, how would you think to modify the theory, taking into account like the non-negligible ratio of viscosities and
well, the integral equations, I only showed, for simplicity, I only showed the integral equation for the limit of viscosity ratio being 0. But you can write down these easily. Write down these integral equations for arbitrary viscosity ratios. And the idea would be to write them for small viscosity ratios and then repeat the analysis in this limit. So in principle, all the ingredients of the theoretical description I've used, you can also be applied if you have two phases.
I was actually yes, I thought about it, but I was actually questioning in my mind what is the impact of the viscosity on the matching with the outer flow. Because I think the outer flow you explained at the beginning, it was like about a singular solution of a vortex line distribute, like of singularities distribute on the vortex line.
Okay. Well, the outer, that's actually only the first order solution.
Yeah.
There's a second order solution which generalizes this. And there are all sorts of technical difficulties. The first order solution has also been done for finite viscosity ratio.
Ah, okay.
Even by G.I. Taylor. So,
Okay.
so G.I. Taylor did a remarkable calculation where he calculated the critical capillary number at which his solution should become undergo a bifurcation.
Okay.
On account of the inner fluid pressing against the tip of the interface, and he calculated a critical capillary number. I just expect that this result is not needs correction, just because, as I've explained, near the tip, Taylor's expression is not correct because the real interface is not conical, but has this slightly more complicated form.
Okay.
The principle in both the inner and the outer expansion, the effect of viscosity ratio can be included.
Okay. That's that's thank you. That's much clearer to me now. Okay, so let's see if there is any other participants who would like to ask a question. Just once again, feel free to unmute your mic if you have a question. Well, that doesn't seem to be the case. So thank you very much once again, Jens, for the very interesting talk and for replying to the questions we had at the end. And I invite our audience to thank our speaker once again. So thanks again, Jens.
Thank you. It was a pleasure.
Thank you. Good evening.
Okay. Bye.
Bye.